Welcome. Today's lesson is about the Td-Mpc algorithm, which is a combination of deep reinforcement learning and the cross-entropy method. So why this lesson about Td-Mpc? First, Td-Mpc is a state-of-the-art method for robot learning because it is sample efficient, time efficient, and it performs well. Also, it is a very flexible and multi-component algorithm as it combines model-based reinforcement learning plus evolutionary methods, here the cross-entropy method, model-free reinforcement learning as an actor-critic method, and representation learning. And I will show you that in this algorithm, Td-Mpc, there is a lot of inner synergy between these components. I also want to mention that there is a previous algorithm which is called Poplin, which is quite similar to Td-Mpc but went less famous. So how will I organize this lesson? First, I will start with just showing you that we can perform model-based reinforcement learning with an MPC component, and then I will show you what synergies we gain by combining this with the temporal difference component and then showing these synergies. So first I will show you that we can get an efficient agent by performing model predictive control on learned models. So in standard model-based reinforcement learning, the agent learns what is called the forward model that predicts the next observation given the current observation and the action. That's an estimate of the transition function of the corresponding MDP, and a reward model that predicts the reward for a given action at a given observation, and that's an estimate of the reward function. And the idea is that these models can be used to predict a trajectory and its return, what is called in imagination, which means without sampling in the real environment, but just performing transitions into the models. One point is that if the transition function is stochastic, trying to predict the next state comes with some irreducible aleatoric uncertainty. So generally, we don't use these models with a too far away horizon. So in time, typically we take 5 steps. And also a point is that when the observations are images, that's complicated to perform this prediction directly. So we need for representation learning, and we will show how to learn this dynamics model into some latent state representation that we will note Z. So in learning model for image-based MPC, we will have first a representation learning component that will transform the observation into latent representation ZT for the observation time t. Then we have a latent dynamics model which corresponds to the forward model but in the latent state dynamics. So given zt and at, it predicts zt plus 1. And we still have the reward model, but this time the reward model will be based on using the latent representation of the observation, which makes more sense. For instance, it is easier to predict the reward if you know that such and such information is true about the environment than predicting the reward just from pixels. And the general idea is that all other learning components that I will show you in Td-Mpc will take the latent state as input. So this representation learning layer is quite crucial in the story. Now, how do we learn this latent dynamics model? We learn it with a consistency loss. So what's the consistency loss? The idea is the following. In fact, there are 2 ways to predict the next latent state. The first one consists in transforming the current observation into a latent state, then asking the dynamics model, given my latent state representation and my action, what is the next latent state? And the other way consists in doing the action in the environment, getting the next observation, and then asking for the latent representation corresponding to this next observation. So after one time step, you can compare the next latent state that you obtain through this way and the next latent state that you obtain through this way and say that these 2 representations should be the same. So you have a consistency loss, which makes the difference between the output of this module corresponding to this way and this module corresponding to this way. And the authors show that just using this consistency loss is good enough to learn a useful representation of the latent state. Now that we have this model, how can we generate efficient actions? To do this, we will use model predictive controls. So what's the idea? From a given latent state, we can generate a sequence of actions and then determine after each of these actions what will be the next state, then determine the reward and evaluate the sequences of actions in terms of how good it is. And then if you generate many such sequences of actions, you can select the best sequence of action, the one that will maximize some value. So with this approach, you generate sequences of action, you evaluate them in imagination through your model by predicting the next latent state through the latent dynamics model and predicting the reward through the reward model. Then you evaluate your trajectories at the reach horizon for some measure. For instance, you can use the sum of immediate rewards along your trajectory, but we will see that this is a quite myopic criterion. And then what you can do is to select the best trajectory. You will use the cross-entropy method that will help you generate better and better sequences of actions. But to do so, you have to start from initial sequences of action and you need to draw them in some way. For instance, you can do this randomly, but here again, we will see that we can do better. Just a quick word about the cross-entropy method because I already explained it into a different video that you should have a look at. So here I will just illustrate it with the idea of sequences of action. So imagine I have a sequence of actions which is parameterized by just two parameters. Around the sequence of action I will use some Gaussian distribution. Here it is viewed from above to determine different sequences of actions that I will generate according to this Gaussian noise. Then I will evaluate the best sequence of actions. Here they are the ones that are in gray. I will remove the other ones. This will help me determine the better Gaussian distribution for the next generation. I will add some additional noise to prevent that my distribution collapses to a single point. This gives me a new generation of potential sequences of action, and then I do this again. And if, for instance, the best sequence of actions is here, where the yellow is the darkest, my population will slowly drift towards population that maximize this reward. So that will be a way to generate the sequence of actions that perform the best. And here the parameters that I optimize to get the best sequence of actions are the actions themselves. So you can see a sequence of actions as a vector of parameters, eventually a matrix of parameters if your actions are multidimensional, and you will just optimize the numbers in these matrices so as to find the best sequence of actions. Note that I have selected best sequence of action. What I will do is that I will just play the first action in the sequence, which leads me into a new latent state, and from there I'm doing the process again. So this defines model prediction control. This is a quite good old approach used a lot in robotics. The idea is that you have selected a sequence of action, you play the first action or a few first sequence of actions that corresponds to something which is called the receding horizon. And since you use your model to predict the next state and you may be wrong, it's better then to play the action in the actual environment to get a better prediction of the current state and to perform MPC again. And you do this again and again until you reach the end of the episode. So with the combination of the cross-entropy method to select sequences of actions and model predictive control, we have an approach that can optimize the behavior of agents. Actually, the first algorithm to do this is called PETS. It presents itself as the first paper combining the cross-entropy method and MPC in the way that I have presented to you. But PETS has a few additional mechanisms. First, it uses ensembling over models to measure some uncertainty, which makes it possible to distinguish aleatoric and epistemic uncertainty and to perform active learning to diminish epistemic uncertainty, which makes it possible to predict over a longer horizon. Anyways, as I have presented to you, the combination of MPC and the cross-entropy method to optimize sequences of actions suffers from a few drawbacks. First, it suffers from a long inference time. You need to evaluate many sequences to find the best one, which is not practical when you are using a real robot. And this is particularly true if you start from random actions because you will take time to find good sequences of actions. Besides, it does not predict beyond the MPC horizon, so it's quite myopic. It may miss something that is very important that happens after the horizon. And I will show you that the temporal difference part improves a lot over these weaknesses. So now we will see the part about adding temporal difference mechanisms to what I have presented to you so far. So what we will do is that we will add two models. One will be a policy that takes the latent state representation as input and provides an action. And also we will learn a critic, so an action value function model that takes the latent state as input and the action, and provides you with the Q function corresponding to this latent state action pair. And that defines Td-Mpc, which adds the temporal difference component to MPC. And as I will show you, it has three synergistic mechanisms. First, the MPC trajectories are used to improve the policy and critic learning. So that's the first mechanism here. With MPC trajectories, you will improve the policy and the critic. Second, the policy will be used to warm start the MPC process with good actions. And finally, the action value function will be used to evaluate MPC trajectories beyond the horizon. This will result in several advantages. First, and that's the main point, the policy network will be able to trigger actions immediately, so we'll get much faster action inference than with standard MPC. Then the combination is less myopic than a single action policy, which is what we would have when using just, for instance, the TD3 algorithm. And also the combination is less myopic than the limited horizon MPC because it uses the Q function here. So finally, the MPC part is faster and performs better because it uses these synergies. So let's have a look at those synergies in more detail. So first, from CEM trajectories, you can improve policy learning. There are several approaches. What you can do is just perform simple behavioral cloning on CEM trajectories to improve your policy. Note that if you do this, you don't improve your critic at the same time. Something which is intermediate between this one and this one is using reward weighted regression, that's this paper, or advantage weighted regression, which is this paper, on CEM trajectories. So what's the idea? The idea is to perform a kind of behavioral cloning where you weight the way to imitate your trajectory depending on its reward value or on its advantage value, which means that you will imitate more better trajectories than worse trajectories, which will help you improve your policy faster and have a policy that performs better than just the cloned trajectories. And the third option is just use pure temporal difference learning from a buffer, but to initialize your buffer with cross-entropy method trajectories, which are better than random trajectories. So you will bootstrap the TD learning process with those trajectories. So in any of the three methods, CEM trajectories will help with more efficient policy learning samples. And doing this is less myopic than standard TD learning because TD learning works on trajectories that are optimized through some horizon. The second synergy is the following. You can use the policy to warm start MPC, which means that instead of playing initially random sequences of actions, you will draw the sequences of actions using your policy with some noise, and that's more efficient than random sampling. In an algorithm that we published, which uses something very similar to Td-Mpc, but using some physics-informed model of the dynamics of the system, we use a mix between playing random actions and policy actions to perform MPC, and we show that this is quite efficient. Finally, the third mechanism corresponds to watching beyond the MPC horizon. So it means that the measure that you take here, instead of being 0, you use the Q value of being on that latent state and playing this action, which summarizes what will happen behind your horizon. The idea is that the action value model summarizes the return of the rest of the episode, and you can see this mechanism as some kind of n-step return. Here you perform the n steps, and here you use the Q function. So it's a way to tune bias against variance, but it's improved because the n steps part benefits from some optimization. And again, this is less myopic than using PETS-like approaches. Now that we have seen all these synergies, how do we put everything together? That's quite simple. So finally, we have those 5 local models, the representation learning layer, the latent dynamics model, the reward model, the value model, and the policy. And what we do in Td-Mpc is that we get samples that we put into a replay buffer with the standard shape of samples in a replay buffer-based reinforcement learning algorithm. From data in this buffer, we get the latent representation using the representation model. And then on those samples, we apply 3 losses. The first one is the latent state consistency loss that I have already explained to you, which is written this way. We also have the reward model that just takes the mean squared error between what the model says and the reward that we observe in the sample. And finally, we have for the value model the standard temporal difference error written in a DDPG-like way, which means that to update your Q value, you take the Q value at ZT+1, and as action, you take the action provided by the policy. And instead of just using the latent state consistency, they combine these three losses to learn a global model, which is called the TOLD model, Task-Oriented Latent Dynamics, which means that some part of the reward and value information are also used to improve the representation. A different way to present exactly the same thing is as follows. Actually, we have a representation backbone which corresponds to the representation model, and we apply those three losses with three different hyperparameters, C1, C2, and C3, where the loss is just the weighted sum of these components. And if you think of the way PyTorch works, just by computing these losses, the fact that the input to these modules correspond to these modules makes it that the losses will be backpropagated up to the representation backbone. So all gradients naturally backpropagate into the representation backbone. A possible different option would consist in considering truly independent modules. So we would just use the consistency loss to learn the representation model, and we would freeze this representation model when backpropagating the other losses. So the representation model would just learn the representation from the consistency loss, and the other model would learn themselves through their own losses. This more independent view is particularly obvious when you learn a policy from states, which means that you don't have a representation learning backbone. And actually, in their paper, they do not compare this idea of freezing or not the representation model when backpropagating the other losses. There are also a few implementation details that need to be presented. First, in their critique, they use layer norm, and this has been shown to be a useful recipe in many recent reinforcement learning algorithms. When the input is image-based, the representation layer uses a convolutional neural network with the following hyperparameters. And note that here they might use more modern vision modules such as DINOv2, the Vision Transformer, ResNet, Siglip, etc. In the replay buffer, they use prioritized experience replay, but a very surprising point is that they rank the samples with the value, which makes no sense. You should have a look there at my video about DQN. And you will see that in fact they should use the temporal difference error to rank the samples. And by the way, they removed this prioritized experience replay mechanism in Td-Mpc 2 that I will present next. And they have many other hyperparameters. In addition to the C1, C2, C3, they have the hyperparameters of the MPC part and the hyperparameters of the temporal difference part, which means that you need a lot of hyperparameter tuning if you want to get something that works well. And also you should have a closer look at the paper because there are a few other details that I did not mention here. Finally, a word about Td-Mpc2. So that's the next version of Td-Mpc. What they do is that they apply it to much larger models with these numbers of hyperparameters, and they add some specific mechanism that makes it that when growing the models, the performance improves, whereas it's not the case with the standard Td-Mpc. And they perform a very large experimental study on many different tasks and task suites. And they show that Td-Mpc2 is better than a lot of state-of-the-art methods. Among the changes, they introduce a SIM norm, they use soft actor critique instead of TD3 as a temporal difference part, they remove prioritized experience replay as I told you, they use an ensemble of Q functions which goes back to the PETS algorithm ID, they condition on task embeddings, etc. etc. Again, have a look on the paper to see more details. Thank you for listening. Don't hesitate to reach me if you have any question. And that's it for today.